this lecture will focus on just some gas laws that you need to be aware of. You need to know how to use them, how to understand them, the relationship between pressure, volume, temperature, number of moles, etc. I want to make one thing very clear that does not, it's not made very clear throughout the text or in the PowerPoints. We're going to have two different volumes we're talking about. The first volume has to do with number of moles that are present. The other volume we will be dealing with is size of container. Okay, those are two very different things, so keep that in mind. All right, so when we start with Boyle's law, there's an indirect proportion between volume and pressure. Okay, so if you look at the differences here in this picture, what you'll see is when the volume is very small, when the mercury coming down here, when it's very small and pushing on this gas to compress it, you see the gas almost can resist and push back on the mercury a little bit. Here, when you push it more with a stronger force, you got to have a higher pressure, you get a compression of the volume. And again, even more pressure here, you get an even smaller volume. So there's an indirect relationship between volume and pressure. Now, as we're talking about the volume here, we're talking about the size of the container, not the number of moles. If you think about the arm of a screen door, that round tube that as it closes the door, the screen door will close very, very gently so not as to slam shut. While air is being compressed, the same amount of air in that tube is there, it's just being compressed kind of like a piston into a much smaller area. And what that does is it slows the rate at which the bar closes. Okay, so as you compress the volume or make a smaller size container, the pressure is going to increase dramatically. You know this if you've ever cooked with anything that has a lid on it. So maybe if you were to be boiling water and put a lid on it, as you boil the water more and more and more, if it were a sealed lid, as the vapor pressure does increase, this is a little bit different because now we're talking about number of vapors, but as the vapor increases, sometimes your lid will start to rattle a little bit, and it's rattling on your pot because there's too much pressure on the lid, more than the lid can stay shut. So with Boyle's law, the mathematical calculation is P1V1 equals P2V2, and this is at a constant temperature. So what do we mean by this? We mean that there's going to be some initial pressure and volume, and it's equal to a constant, and there's going to be some alternate pressure and temperature. A change is going to occur, and that's also equal to a constant. So what we can say is an initial pressure times an initial volume equals a final pressure times a final volume. So if we look at this example, if a skin diver takes a breath at the surface, filling his lungs with 5.82 liters of air, that's our first volume, what volume will the air in his lungs occupy when he dives to a depth where the pressure is 1.92 atm? That is our second pressure. How do I know it's the second pressure? Because he's at the surface taking in air, and then eventually there's going to be a change, and the change is the new pressure of 1.92 atm. So the pressure at the surface at sea level is 1 atm. So we have here our initial volume, initial pressure, our final pressure, and they're asking us what V2 is going to be. So we're given an initial and final volume and pressure, and then a final pressure. So if I just plug and chug solving for V2, I literally just plug in all my given information. Keep in mind, your units have to be matching. we must be using ATM and we must be using liter. So for example, if you were given milliliters, you would have to convert that. If you were given millimeters mercury, you would have to convert that. Plugging and chugging, we get 3.03 liters. Now, the question I want you to ask is this a reasonable answer? Well, the answer is yes, because if we started off at 1 ATM, a lesser pressure with a higher volume, again, meaning container, not number of moles present or molecules present. As soon as we increase that pressure, we would expect the volume to drop, just like within a piston. So Charles's and Gay-Lussac's law, there's a direct proportionality between temperature and volume. So as the temperature increases, the volume increases. We see this all the time in our everyday living. You heat something up, it expands, it goes further out. So we have a direct relationship here with absolute zero. At absolute zero, you will get zero volume. And absolute zero, I just want you to recall, as part of that Kelvin scale, is 273.15. So Charles and Gay-Lussac's law talk about a direct proportionality between volume and temperature, where there is a constant, and in this case, the constant is pressure. So Boyle had a constant temperature, and pressure and volume were changing. Charles and Gay-Lussac's law is volume and temperature are changing, but the pressure is remaining the same. So we can say that V1 over T1 equals V2 over T2. Similar setup to Boyle's law, but now because it's directly proportional, it's V1 over T1 equals V2 over T2. And all the temperatures must be in Kelvin. So for example, a sample of argon gas that originally occupied 14.6 liters at 25 degrees Celsius is heated to 50 degrees Celsius at constant pressure. Constant pressure is your clue that this is Charles's and Gay-Lussac's law, okay? It's giving you an initial volume, two temperatures, a initial and final temperature, and it's asking for the new volume or the final volume. So we have to convert both temperatures to Kelvin, and 25 degrees Celsius is a standard degree Celsius, and that is just 298.15 Kelvin. And the second temperature, 50 degrees Celsius, you just simply add 273.15 to get it into Kelvin. If you don't remember how to do this, go back to the first couple of weeks of lecture when we talked about conversion. And then the volume we can leave the same because it's already in liters. So now just solving for V2, we get V2 equals V1 over T1 times T2, plug, chug, and literally get your answer. It's that simple. I think a lot of you are going to find the gas law problems are probably going to be the easiest thing for you this whole semester. Now we have Avogadro's law, and this is a direct relationship between volume and moles at both a constant temperature and pressure. So we're going to have volumes and moles, and what we can say is the relationship between volume and moles is equal to a constant, again, temperature and pressure. So we can say V1 over N1 equals V2 over N2, right here. And this proportionality amount, we're going to work with this a little bit differently than we just plugged and chugged with the previous ones. So if, for example, here we had a reaction between hydrogen gas and nitrogen gas, we would find that you get two ammonia, NH3s. So you have 3H2 to 1N2 to 2 NH3, just based on this balanced chemical reaction right here. By saying that with this 3 to 1 to 2 ratio, what we can say is 3 molecules to 1 molecule to 2 molecules. We can say 3 moles to 1 mole to 2 moles. We could say 3 liters to 1 liter to 2 liters. It's the ratio that matters here. So if we look at this problem, it says if we combine 3.0 liters of NO and 1.5 liters of O2, and they react according to the balanced chemical equation, 2NO plus O2 yields 2NO2, what volume of NO2 will be produced? Assume that the reactants and products are at the same temperature and pressure. So remember, with Avogadro, temperature and pressure being the same is the constant. So that's your clue that this is an Avogadro's problem. So it says apply Avogadro's law to determine the volume of a gaseous product. So here we go. We know there's 2 to 1 to 2 ratio. And we know that based on the balanced chemical equation, the volume of NO2 is equal to the volume of NO. So that means if 3 liters of NO reacted, you'll get 3 liters of NO2 because of the ratio between them. Now we have the combined gas law, and this is literally just like what it sounds. It is taking all of the previous gas laws we just did and combine them into one gas law. And it is P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, little trick here. The only time you need to include the N in this equation is if there are different number of moles. Lowercase italicized n means moles. If they don't give you a mole or a mole amount, you can make the assumption that all the moles are equal and you don't need them in there. If you really, really, really want to use it and they don't give you a mole amount, throw a 1 in there, okay, for a numerical value. For the most part, though, this is what you're going to be using unless the moles change based on whatever problem you're given. So, if a child releases a 6.25 liter helium balloon in the parking lot of an amusement park where the temperature is 28.50 degrees Celsius and the air pressure is 757.2 millimeters mercury, what would the volume of the balloon be when it has risen to an altitude where the temperature is negative 34.35 degrees Celsius and the air pressure is 366.4 millimeters mercury? So, what we have here is we have 2 temperatures, 2 pressures, 1 liter, and we're given no information about moles. When we're given no information about moles, we can assume the moles stay the same, and we will completely ignore the N in the equation. You have to convert the temperatures to Kelvin. They must be in Kelvin. If you look here, they have not converted to ATM. You can convert to ATM. It just is going to not give you the exact correct answer. So keeping it millimeters mercury, as long as they are both millimeters mercury, you're good to go numerically. It'll cancel out because of the ratio between millimeters mercury and ATM. So literally just plugging and chugging, what you get is the the pressure, temperature, volume, pressure, temperature. Everything cancels out. You're left with the new volume. So it should make sense that your volume increased.